Thanks for joining me in my studio today. My name is Carl and I have been presenting training on solar and solar design and installation for the last probably about 15 years. Today we are going to be taking a look at sizing and designing lead acid batteries. Despite the massive drop in price for lithium ion batteries, we see a lot of Facebook requests about questions on sizing and designing lead acid batteries. So today's video is to try and give the guys that are still looking at lead acid batteries a peek into sizing and designing lead acid batteries, the pitfalls, what you need to look out for, and what you can do to make your lead acid battery bank last longer. You are going to get access, might be above this video, there should be a link to a document called generic data sheets. There you can see it at the top of the page. And the generic data sheet document contains a whole list of data sheets where the brand names in the data sheet has been removed. In most of them, the model number is still available. By and large, the data sheets are generic, so they're non-branded. We are going to be spending most of the course in pages B4, B5, and B6. We might look at page B7. Let's quickly take a look at what C ratings are. So let me explain it before we take a look at the data sheets. The C in C rating means capacity. And the C rating explains the capacity of a battery over a specific period of time. With lead acid batteries, the C rating is normally indicated as a C20, for example. The C refers to the capacity of the battery, and the 20 is an indication of time. Let's quickly take a look at where this appears in data sheets and what this looks like. In your data sheet on page B4, at the top of the page, it gives us the capacity of the battery. So there it says the capacity of the battery in amp hours. So on the right-hand side of this table shows the capacity in hours, and on the left-hand side shows the capacity in minutes. We're going to be focusing on this side of the page, or this side of the table. What the data sheet shows is 20 hours, 200. I'm just going to write this down. Let's just focus on the screen quickly. The data sheet gave us three values: a 20-hour value, a 10-hour value, and a 5-hour value. It doesn't give us anything less. So you will find with some other batteries, if the battery, this is deep cycle, which means it's supposed to be discharged over a longer period of time. You do get other batteries that are more UPS type of batteries where the discharge rates will be shorter. So you might end up with a 1-hour rating, and you'll end up with less than 1-hour ratings. In fact, in the data sheet on page B4, we'll see the data sheet has the capacity indicated in the top part of this table. So I want to write it down quickly. It says that if we look at the 20-hour rating, so if we look at the 20-hour rating, the battery has a capacity of 200 amp hours. If we look at the 10-hour rating, the battery has a capacity of 171 amp hours. And if we look at the 5-hour rating, it says the battery has a capacity of 157 amp hours. It goes on towards the left-hand side of the table where it talks about the capacity in minutes. So then it says at 75 amps,
So then it says, changes the way it provides information. Now it says at 75 amps, this battery is going to last for 110 minutes. And then it says at 25 amps, it says this battery is going to last for 389 minutes. So it gives us different values. Let's explore them quickly. On the left-hand side, before we close the screen, on the left-hand side, we see CCA. CCA is short for cold cranking amps. Now, when we buy a car battery is rated in CCA. Because these are blanked out, it means that this battery has not been manufactured for starting cars. So there's a unique difference between how the plates have been manufactured or how the plates are structured when we look at car batteries and when we look at deep cycle batteries. This slide shows us the difference between a car battery positive plate and a deep cycle battery positive plate. We can see when we look at these plates, we can see that the way they've been manufactured is different. So the car battery has all of the lead, has all of the lead in the plate structured in such a way that it almost points towards the terminal. Whereas in a deep cycle plate, we don't see that same type of architecture. So there's a difference between a deep cycle and a car battery plate and the way in which they've been manufactured. So what the data sheet is saying is if we are discharging the 200 amp hour battery, so we go to a store, we buy a 200 amp hour battery, we ask for a 200 amp hour, they give us a 200 amp hour battery. The capacity of the battery is linked to a specific rate of discharge. What we can do over here is we can compare this to cars, for example. The capacity of the battery is affected by how hard we are trying to make the battery work. If we do the same thing and we compare that to cars, we stop at a fuel station, we ask the attendant to put in, to fill up the car. He fills up the car, the car has a 40-liter tank. If we drive carefully, we end up getting 600 kilometers per tank. If we make the car work harder for the same capacity, maybe I should change the way I've written this, and that gives us 15 kilometers per liter. If we fill up the same, we fill up the car again with 40 liters. This time we drive faster or we drive harder. So instead of 600 kilometers, we only get 400 kilometers out. And that gives us 10 kilometers per liter. So how we drive the car determines how far we go on the same amount of fuel. So when we buy a battery, we've got a 200 amp hour battery. So we've got the capacity to drive further. We've got the capacity to drive less. And that capacity is affected by how we drive. So when we buy a battery, we have the same capacity because the battery is a specific size, or we have the same size battery. Maybe that's the right way to say it. So we have the same size battery, but the capacity of the battery is going to change. Maybe the word to use is potential. The car has the potential to reach 600 kilometers on a tank of fuel, but our capacity is affected by how we drive. So the battery has the potential to give us 200 amp hours, but the capacity is affected by how we use the battery. So we've got the same potential because of the 200 amp hours being 200 amp hours, but how much we get out is affected by how we use it. So if we have a 200 amp hour battery and we are going to be discharging it over a period of 20 hours. So in the term over here, you'll see we have a time allocation. So amp hour consists of 2 units, amps and hours. When they give us the hour rating, what we can do is to take the hour rating and divide it by the amp hour value. And that will tell us what the anticipated rate of discharge is. So what they're saying is if we discharge this battery at a rate of 10 amps for 20 hours, it'll give us the full capacity of the battery. So 10 amps multiplied by, this would typically be a 12-volt battery, equals 120 watts. Maybe, oops, what we should do, 10 amps times 12 volts equals 120 watts. Then it all ends up on the same board. Okay, so 20 hours multiplied by 10 amps. 200 amp hours divided by 20 hours equals 10 amps. We multiply the 10 amps with 12 volts because it's a 12-volt battery, and that gives us 120 watts. So what the data sheet is saying is if we are going to be discharging this 200 amp hour battery at a rate of 120 watts, it'll last for 20 hours and then it is completely discharged. Now, if we go back to the data sheet, we'll see that the data sheet says the state of charge, but on open circuit voltage, the state of charge when the battery is completely discharged is 11.64 volts. So what these guys are saying is that once we have discharged this battery over a period of 20 hours at a rate of 120 watts, we take a multimeter and we measure the potential voltage over the cells or over the 2 terminals, we'll end up with plus minus 11 volts. So this, according to the data sheet, means the battery is completely discharged. So that gives us 120 watt discharge rate. Okay, so what have we been doing in industry? What do we see in industry? We see a guy fitting a 5 kilowatt inverter to a customer's loads, and we see them fitting 4 batteries. That's 3. You see them fitting 4 12-volt batteries, connecting them in series to generate 48 volts. And we see the 4 48-volt batteries connected in series to a 5 kilowatt inverter. this is what is typically happening in industry. We see guys typically using the expert range of inverters or the Voltronic inverters. A 5 kilowatt connected to 4 batteries connected in series. The issue that we've got over here is that according to this, if we wanted this battery to last 20 hours, we shouldn't discharge at a rate faster than 120 watts. So what it's, let's quickly take a look and see what happens in a typical load shedding scenario. So load shedding scenarios vary between 2 and 4 hours. The smallest value they give us over here is a 5-hour scenario. So they do give us values here and values there. They say 75 amps, the battery will last 110 minutes. Load shedding is 120 minutes, typically, depending on the type of cycle that you're on. So that is less, and this is to completely discharge. So lead acid batteries, we don't want to discharge less than 50% of its rated capacity. So what I'm going to do is I'm going to wipe the minute section out because that, or what we are trying to achieve, is not applicable. If we wanted to discharge the battery over a period of 5 hours, which is going to be more or less a 2-hour load shedding cycle, because remember, we need to factor some losses in. So 2 hours will go towards load shedding. We'll have 2 hours remaining. So this battery will be at plus minus 50%. Going to be a bit more, but in a load shedding cycle, if we discharge this battery over a 2-hour period, we'll end up with roughly 50% of the capacity of the battery left. I'll try and cover this again a little bit later. So let's just look at what is happening here. So 157 amp hours divided by 5 hours is equal to 31.4 amps. If we had 4 batteries, how would that be affected? So if we take the 4 batteries and we connect them in series, that's going to give us 31.4 amps multiplied by 48 volts, 1.5 kilowatts. What the data sheet is saying, the data sheet says, if we take these 4 batteries, we are discharging them at a rate of 1.5 kilowatts. These batteries will last 2 hours. And then they'll be at more or less 50%. I know over there it says 5 hours, but we allocate some time for losses. So in this case, we'll just leave 1 hour for losses. We've got 5 hours of discharge. A 200 amp hour battery becomes a 157 amp hour battery if we discharge it over a shorter period of time. So same scenario we had there, but in this case, only with lead acid batteries. So 1507 is the maximum rate of discharge, and then we'll only have 2 hours of power. Okay. And what if we are creating a solution for a customer that is in an off-grid environment? So in an off-grid environment, we want to discharge the battery over a longer period of time. So let's just play with that concept quickly. So not load shedding, off-grid. So off-grid, we take a 200 amp hour battery in an off-grid environment. The customer goes to bed at 8 o'clock in the evening. We want the power to last until 6 o'clock the next morning. That gives us roughly 10 hours. But this is 10 hours from completely fully charged to completely empty. So if we wanted the battery to be discharged down to 50%, theoretically, we can't work on anything smaller than the 20-hour rating. So let's disregard the 10-hour rating because that's in an off-grid installation, that's not going to be applicable. So we want to discharge for 20. We've got the ability, so it's got the potential to discharge at that rate over a period of 20 hours. But if we want to still have 50% depth of discharge, if we want to have a 50% depth of discharge, then we will only be able to discharge at that rate. So we'd be able to discharge at a rate of 120 watts for 10 hours. Guys, and then this battery will be at a 50% depth of discharge. Let's quickly jump back to the data sheets. There's something that I want to just mention quickly. So what this data sheet says, this is the same battery. What it's saying is if we discharge it down to 50% depth of discharge, so this is now on the next page, page B5, saying if we discharge it down to 50% depth of discharge, this battery is going to give us 1,750 cycles. So discharge at 120 watts for 10 hours, 50% depth of discharge, 1,750 cycles. So that would be the equivalent in an off-grid application, 1750 divided by 365. That'll be roughly 5 years. So plus minus 5 years is more or less how long the battery is going to last. If we were to take 4 batteries, we take 4 batteries, we connect them in series. So that 10 amps now becomes 48 volts. That is 480 watts. So if we discharge the batteries at a rate of 480 watts over a period of 10 hours, the batteries will be at 50% depth of discharge. It'll have a remaining 10 hours of capacity, but we can't discharge it at less than 50%. Now, if we increase this, what if the customer has a bigger demand? In order for the customer to discharge at a faster rate, we need to increase the batteries. So we need to be able to have a few more batteries. Let's just see, 1. So we add another bank. We connect these in parallel to those. So those batteries are connected in series. That bank is connected in series. And then these 2 banks are connected in parallel. So what do we have now? Now we have, instead of a 200 amp hour battery bank, we now have a 400 amp hour. So where do I write that? That gives us 400 amp hour, 48 volts. So now we can discharge that bank at a rate of 480 watts, and we can discharge this bank at a rate of 480 watts. So that can be added, and that gives us a rate of 960 watts. So now we can discharge at a rate of almost 1 kilowatt for a period of 10 hours until we reach 50% depth of discharge. Let's use a different battery and see what we get from something else. If we take a look at the next battery in the data sheets, this is a different lead acid battery. For this battery, we'll see that the way they provide the information is slightly different. They give us, in this part of the table, they give us the hour ratings. In this part of the table, they give us the minute ratings. I don't see cold cranking amps, so still not a car battery. And then at the bottom over here, they give us some interesting values. Now guys, every battery you buy will have a different data sheet. So you've got to find the data sheet for the battery that you're working with. If the battery that you are working with doesn't have a data sheet, then buy a different battery. Because you need this information to be able to do your calculations correctly. So what this particular data sheet, let's just see what this thing says. Let's explore this first. Over here it says charge rate and discharge rate. Maximum continuous and then recommended maximum continuous. So the recommended maximum continuous is 0.5 C10HR. Recommended for that battery is 0.5 C10HR. 0.5 C10HR. So that means that it is 0.5 times the capacity of the 10-hour rating. I know I've just, so let's just write that out. 0.5 times the capacity at 10 hours. So let's quickly take a look at what that rating is. We'll see that the 10HR value sits over there. So what it's saying is at 10 hours, the 100 amp hour battery becomes a 95 amp hour battery. So in this data sheet, we can see the same thing mirrored that we saw in the previous one. So if I get back to cars, the battery has a specific amount of potential, but the capacity of the battery is determined by how hard we make it work. In the data sheet, it shows that the recommended maximum continuous rate of discharge is 0.5. Let's just take a look at the rate of discharge first. We'll take a look at the rate of charge shortly. So 0.5 C10HR, they already told us that the 10-hour rating (95 amp hours). So we divide that by 10 hours, and that gives us 9.5 amps. So what they are saying is that 0.5 times 9.5 amps equals, what is that, 4.75? 4.75 amps. So 4.75 amps multiplied by 12 volts equals 57 watts. Wow. Equals 57 watts. If we were to have 4 of these batteries in, if we were to have 4 of those batteries in series, that would be 4.75 amps multiplied by 48 volts, and that would be 228 watts. That's if my maths, yeah, that's correct. 228 watts. So what they're saying is if we discharge, we have 4 batteries, these 4 batteries connected in series, we can discharge at a rate of 228 watts. So 4.75 times 48 volts equals 228. So if we needed to discharge at a faster rate, so guys, these are 100 amp hour batteries. If we discharge it at a rate of 228 watts, how long will it last? It's only going to last 5 hours. It'll last 10 because we use the C10 rating, but we can't discharge down to 0%. So we've got to leave 50% depth of discharge. So we'd be able to discharge at that rate 5 hours. Wow. Okay, so we could add another bank. If we add another bank, so if we add another bank, it would be 228 plus 228. It would still only be 500 watts. That's not very good. No. Okay, so that is if we use a different type of battery. So this is for 100 amp hour battery. So if we wanted the battery to last longer, we would have to reduce the rate at which we discharge the batteries.